At first, let me introduce myself in 4 words. First of all, I got married in Cannes, so that's very special for me. Secondly, I work at Neo4j. Thirdly, I love graphs. Everything is graph. Graphs are everywhere for me. And I will talk about graph embeddings. So let's start and tell a word about the agenda. So we will present rapidly Neo4j company, the graph company. Next, we will handle graphs and AI. So with the Neo4j Graph Data Science Library, we will define graph embeddings and especially node embeddings. And we will look after the use cases that are enabled by this technology. Then there will be a nice demo and a conclusion and key takeaways. So let's start with the graph. So anything can be a graph. A graph is connected data, nodes and relationships that connect them together. A first graph can be the internet with HTML pages being linked through HTML links. A water molecule, atoms connected together. The metro stations connecting through lines, and social media, social relationships. And the intuition here is that connections is better than collections. Connections in data are as valuable as the data itself. And we can speak about networks of people, transaction networks, knowledge networks. The complexity of the world, the complexity of your enterprise context is better captured through a graph. The graph model better defines your use case and your context. Neo4j company in a nutshell. So we are at the origin of the graph sector. And we are the graph market leader. We have thousands of customers around the globe with lots of downloads, a large community of 230,000 people that already use Neo4j. So either developers or data scientists. We raised the largest investment in database history in June 2021 with $19 million in F series, and we have customers among the top 10 retailers, aircraft manufacturers, all the top 20 banks in North America, telcos as well. How Neo4j differentiates from other databases where, well, we are graph from floor to ceiling. So the storage is natively a graph. So connected data are stored contiguously. In terms of processing, we have a graph process engine. We have a graph language for queries, which is Cypher. I will say a word about that. And we have graph visualization, especially with Bloom. So in short, graph specialists. And about the graph query language, well, I just told you that I got married in Cannes. And this is a graph. This is a quick graph, a connection. And we could replace the two nodes here with parentheses, dash dash superior, and this is Cypher. You have understood that I have drawn here a node connected to another through a directed relationship. And now I can add some match clause to get a result, and also I can add the relationship type. What is the Neo4j graph platform? Well, it is composed of the Neo4j transactional database at the core. This Neo4j database is augmented with graph analytics. Data integration modules exist, say, for example, the Kafka connector for real-time data, also the Spark connector, and as well the BI connector. Data analysts and data scientists will use the GDS plugin to compute algorithm results such as centrality, community detection, similarity, and so on. And developers and admins will connect to the database using official drivers and APIs, in particular the Grand Stack. And as for business users, they will use ad hoc user interface or Bloom visualization tool. About graphs and data science, well, we could say that it is the convergence of machine learning, visualization, and queries. With queries performed through Cypher language, you will find the patterns you know exist. With machine learning, you will try to uncover trends and make predictions through algorithms and machine learning models. And with visualization, you will explore, collaborate, and explain. So what is the difference between queries, algorithms, embeddings? Let's explain. Well, queries, you have an intent. You know the exact relationship and data you're looking for. But there can be overly complicated global queries. It can spin if you perform pattern matching on the whole graph. And yeah, so locally it works if you have an anchor in the graph. But if you want to find global patterns, then you have to use algorithms. So this time you know the kinds of patterns you're looking for, most central nodes, shortest path, and so on. And you can choose the right algorithm and parameter tuning. For embeddings, a little bit more complex, you will create a highly predictive graph format for machine learning. It's a very interesting feature. So you know there's significant data in the graph, but it's unclear what to look for. And the results aren't human readable or interpretable. So very different queries, algorithm, embeddings. But let's explain what are graph embeddings and node embeddings in particular. So what are node embeddings? This is a representation of nodes as low dimensional vectors that summarize their graph position, the structure of their local graph neighborhood, as well as any possible node features. And how is it obtained? Through an encoder-decoder framework. So let's explain what exactly is a node embedding. It is a vector, so a feature representation in low dimension. And this vector is the result of an encoding function. The encoding function takes the node as input and it produces a vector. What is extremely crucial here is that the similarity of embeddings between nodes is reflective of the similarity in the actual graph. So for example, we would have the karate graph here and the representation in dimension 2, so 2D embeddings. And so the proximity, the similarity between nodes, the proximity in 2 dimensions would be reflective of the similarity of nodes in the graph. So red nodes should be closer together, and blue nodes, violet nodes, green nodes as well. So which means that we have to encode the nodes such that the similarity in the embedding space, for example cosine similarity, which works well with vectors, approximates best the similarity in the graph. We have in the graph data science library provided by Neo4j 3 graph embedding techniques. First one is node2vec. It's a random walk based embedding that can encode structural similarity or topological proximity. It's quite easy to understand and is really interpretable with parameters, plenty of examples. It is the most known embedding algorithm. Then on the far right, there is FastRP. It's super fast, it's based on linear algebra, and it can encode topology or properties or both. And it's 25,000 times faster than Node2vec, extremely performant. And FastRP extended encodes the properties as well. Then there is GraphSage. It is a little bit different. It uses inductive embedding, and it encodes properties of neighboring nodes when learning topology. And it can be generalized to unseen graphs, so which means that you can use GraphSage for incoming data, and you don't need to retrain to re-execute your embedding algorithm. So that's an advantage of GraphSage for new data. So what are node embeddings for? Well, they can be used to compute similarity between nodes. They can be used for to be visualized in 2D plots, like we saw just before with the karate graph. And also they can be used as features for machine learning models and to compute neighborhood prediction or node classification. Now let's talk about the use cases enabled by graph technology and especially node embeddings. Graph technology and graph embeddings are a technology useful in different fields, and we would say decision analysis, customer experience, data unification, personalization, and discovery. In each of these areas, we will highlight 5 use case categories that leverage graph embeddings: fraud prevention, behavior prediction, data disambiguation, product recommendations, and drug discovery. So let's explain why graph embeddings can be used. First of all, in fraud detection, that can be used to distinguish normal transactional from fraudulent behavior by encoding the behavior of normal and abnormal accounts and training a predictive model to distinguish them. About disambiguation, by encoding each node and its context in the greater graph, its properties, neighbors, their neighbors, and so on, you can use basic math to identify nearly identical embeddings, thus reducing numerous several profiles to just one person. About product recommendations, well, an embedding can encode not only what someone bought, but how many other things that person bought. Who else bought those things? What else those people bought? And so on across the whole graph. So in a very large product catalog, graph embedding supports strong recommendations because they mathematically highlight closely related items, even if those items are rarely viewed. About drug discovery, well, systems biology is naturally graphy. The connections between genes, chemicals, and diseases encode the causes and cures for myriad conditions. Graph embeddings can encode this information: how each gene is connected, how far away, and via what intermediate nodes to a disease, or what chemicals might modify genes by direct interaction or interference with upstream pathways. These rich and descriptive embeddings can be used as input for link prediction models. These models use existing knowledge to uncover previously unknown associations between genes and diseases or drugs and genes, and thus identifying promising new treatments. Last but not least, predicting churn. Well, the context of the customer can include interactions with other customers and all their interactions with the provider, previous purchases, store visits, customer service calls. So we can encode that rich detail as a knowledge graph and train embeddings to represent each customer's experience, and then use those embeddings to predict who is likely to leave a service, so early intervention can save the business. Which customers make use of graphs and graph embeddings? Well, top 10 banks to recover more fraud. And the challenge is about missing over 85% of synthetic identity fraud. And we use advanced graph queries and scalable community detection algorithms to uncover fraud networks. The results? Well, over $20 million in lost savings in first year. But Meredith Corp, the challenge was to have 14 billion of anonymous data points and turn them into 163 million unique user profiles. And the result is that using the graph data science and especially embeddings, the user profiles get more personalized recommendations and drove 612% increase in web traffic. The last three use cases, so eBay for the recommendation engine category. The challenge was to search through 20k plus products with 150k plus attributes, and eBay chose Neo4j as a native graph database to understand the conversational shopping scenario. And as a result, the eBay app now provides truly customized recommendations to their customers. Regarding drug discovery, we have the Novartis use case. The challenge was to find associations across vast experimental data and medical research, and the solution was to create a knowledge graph that captures the biological knowledge linked to research. And then Novartis was able to identify promising compounds to accelerate drug development. And regarding customer churn, we have a telco customer that we cannot name, whose challenge was to understand why customers churn and how to react proactively before. The solution was to create a Neo4j graph that captures every customer interaction with the operator and even between the customers, and to detect early warning signals thanks to Neo4j graph data science library, especially graph embeddings. The results are customized marketing campaigns for at-risk customers that reduce churn. Let's go with the demo. Let's proceed. So we will explore the Marvel domain. So with superheroes, comics, groups, events, battles, and so on. So let's imagine that I am a superhero character, and I interact with other characters who are my enemies or allies. So I participate in events, I appear in some comic books, and I'm part of groups such as X-Men. And I have statistics such as intelligence, durability, strength, and so on. Let's explore one of the characters who is a real one, not me. So let's find Logan. So here, so Logan, we could expand his statistics. So Logan has a high fighting skill. On the contrary, his energy and intelligence and speed are pretty lower than other characters. Who are enemies of Logan or allies? So we can recognize Black Widow, Punisher, Elektra, and if we go to see his enemies, let's find, for example, Magneto here, or Mystique. Okay, you can see the point, and Logan is part of the X-Men group. So let's reveal the group is part of. Okay, the X-Men and the other X-Men are part of this huge group. So we're gonna try to explain and to predict whether characters that are not labeled as X-Men are in fact X-Men. And we also gonna try to perform link prediction. So let's go to the Neo4j browser. Here we were in Bloom and trying to explore visually and intuitively the graph without writing down a line of cipher. On the Neo4j browser, we're gonna follow a Neo4j guide here, and we're gonna load a graph to perform class prediction, so node classification. What is our graph projection? So we will project a part of the graph that is stored in the disk in the Neo4j database in the memory. We are not gonna project all the data. We're gonna project only the character nodes with some properties we have computed, and especially an embedding. Let's look at what is an embedding. As I said before, it's a vector. Okay, a vector of floats. Let's spin this guide on the top. So we're gonna project some properties: durability, intelligence, energy, whether it is a known X-Men or not. And yeah, we have some model data and as well some holdout data. And the relationship appeared with are gonna help us to predict the class. So let's project our graph in memory. So we have our graph here in memory. The next step is to train our model with our feature property, which is fast RP embedding, and our target property is X-Men. So we have trained our model, it's pretty good. We're gonna also train another model with only tabular properties, so they are not extracted from the graph. It's not a graph embedding, only energy, speed, strength, and so on. So less performant. So let's now predict if we have more X-Men and check our predicted node classes. So in effect, Steve Rogers, James Buchanan, maybe X-Men as well. We can also train a link prediction in Neo4j. So we will here split the graph into the data we want to use for the model and the data to hold out to test afterwards. So we split the model according to the years. So that's it. And then we load a graph for class prediction, including the characters with fast RP embeddings as well, and the appeared with or appeared with holdout, because our data set is split between train and predict data. What happened here exactly? Yeah, let's go back to where we were. So we load the graph for class prediction. Okay, and then we split between test and split in memory in the in-memory graph. So we train our link prediction model. and we could still compare with a model that does use strength, speed, so tabular properties here. So the train and test graph score are pretty lower than with the embeddings. And then we want to predict if a specific character appeared with a predicted X-Men. So let's go with that last query, and then we check the predicted links. So what happened here? Yeah, here. So Maxwell Max Dillon should be linked to John Walker, and if we go back to the end, let's group by number of suggested characters to appear with. And here we have Maxwell Max Dillon linked with those other characters. And our models were more performant with graph embeddings, whether to perform node classification or to perform link prediction. As a conclusion, 3 key takeaways. First of all, Neo4j acts in your information system as the core data management module, connecting your data silos together and finding new insights. And it can be hosted anywhere on-premise, in the cloud, AWS, Azure, or GCP, or as a service, a DB as a service named Aura. Secondly, your graph ecosystem will rely upon a Neo4j database, the native graph database with persistent data. Secondly, Neo4j Bloom to visually and intuitively explore your connected data. And then the graph data science library that augments Neo4j with scalable graph algorithms and machine learning models. And thirdly, you can use graph embeddings, and especially node embeddings, to compute similarity between the nodes in your graph, and thus enabling to disambiguate user profiles on the internet, or discovering new drugs, and so on. And you can also use your node embeddings to represent your graph in 2D plots, but also use node embeddings as features to train graph machine learning models and perform node classification or neighborhood prediction. So that's it for me. Thank you very much. And one last piece of advice: don't lose time to make use of your connected data, and live in a real connected data company. Use Neo4j.